Hello everyone, welcome to the extra session of this tutorial and of this Sobolev and Bachelor of Engineering Equations. My name is Shami and currently a PhD scholar at the Department of Mathematics. In today's extra session, we will discuss uh, mainly about the strong maximum principle, and that involves all the sort of basic whatever theory we did in this course. So it will be a bits and pieces of every week a little bit, uh, and moreover it actually proves we will prove strong maximalism in one dimension, and that shows the an idea like how things actually works when we have dimension one case. So without further ado, let me start the today's tutorial. It's all about strong maximum principle. So we will have some parts. So we prove this whole principle in bits and pieces. So for that, we will consider the bilinear form. So consider the bilinear form AUV equals integration 0 to 1 P U dash V dash plus Q times UV, where P belongs to C1, 0, 1, P is greater than equal to alpha positive on 0, 1. So P is a positive function, positive C1 function, and Q belongs to be a continuous function. We assume that A is cohesive or H naught 1 omega. And moreover, note that we are not making any sign assumptions on Q. So given F in L2 0 1 and let U2 be in H2 0 1 be the solution of minus P U dash whole dash plus QU equal to F on open interval 0 1. And then we have U0 equal to U1 equal to 0. Assume that F is greater than equal to 0 almost everywhere on 0 1, and F is not identically equal to. So our goal is to prove that U dash 0 is positive and U dash 1 is negative. And one more thing, that Ux is throughout positive for all x in 0 1. Name this to be 2. I'll name this to be 3. So the first part is assume that size in H1 0 1 satisfies a psi v less than equal to 0 for all v in H0 1 0 1, v2 v greater than equal to 0 on 0 1, psi 0 to be less than or equal to 0 and psi 1 is less than or equal to 0. Prove that psi has to be less than or equal to 0 on open interval 0, 1. So basically we are trying to prove that if you have a function psi, for that we have which is actually non-positive on the boundary and has the value to be again non-positive with respect to the with the bilinear form, then that function has to be non-negative only, non-positive only. So how do we show that? Put v equal to psi plus in 4. So we can put v psi plus in 4 because I know that the uh, psi is non-positive on the boundary, so then psi plus has to be 0 on the boundary. So this will implies since v0 and v1 both are 0, so this actually implies v is in h naught 1 x 0 1. So once that is the case, when we put this to be there, we have a psi v is less than equal to 0. This implies the integration 0 to 1. Integration 0 to 1. And what was my a? My a was nothing but this form. So p psi dash v dash plus q psi, and then v has to be less than equal to 0. But this basically implies 0 integration 0 to 1 p psi is psi plus minus psi minus whole derivative, and v is nothing but psi plus derivative plus q psi into psi plus minus psi minus. This is less than equal to 0, and then psi plus and psi minus has support which actually contains just only that set. Basically that is empty only, or we have there where both are 0 only. So this actually implies this will just psi minus and psi plus, the integration over of psi plus and psi minus will be 0 only. And since that is the case, we have integration 0 to 1 p psi plus whole derivative again psi plus whole derivative plus q psi plus into psi plus, which is less than equal to 0. So what this basically implies, now we have this is nothing but a of psi plus and psi plus, which is less than equal to 0. And here now we can use coercivity, using coercivity of a, we deduce alpha times the norm of psi plus whole square. It has to be less than equal to a of psi plus and psi plus, which is less than equal to 0, which eventually implies the psi plus square has to be less than equal to 0. And once that's the case, this actually implies that psi plus is actually equal to some constant almost everywhere. But since I know is in h naught 1 omega, we can use Poincare, implies psi plus has to be identically equal to 0, or basically equal to 0 almost everywhere. And once that is there, we have our result. This will implies psi has to be less than equal to 0 almost everywhere in 0, 1. Again, these are continuous functions in the one dimension, so I can write this as well because of the embedding in the one dimension. Okay, so far so good. Next, consider the problem. So let me name it to be 5. It says minus p zeta dash whole dash plus q into zeta equal to 0 on open interval 0, 1, zeta 0 equal to 0, and zeta 1 equal to 1. So when I consider this problem, we have the second part, which is show that 5 has a unique solution zeta, and that zeta is nothing but non-negative on open interval 0, 1. So solution. So I can consider since zeta I know is on the boundary at 0 it taking value 0 and at 1 it taking value 1, then I know if I consider the zeta minus at 0 and as well as zeta minus at 1, both have to be 0 only. But this implies that zeta h minus actually lies in h naught 1, 0, 1. But what we will try to do, we just plug in the zeta minus as a test function in 5 as a test function. In 5 we obtain we actually end up with minus 0 to 1 p times zeta dash whole dash into zeta minus plus integration 0 to 1 q theta into zeta minus equal to 0. So by integration by parts, what we deduce that this is nothing but integration 0 to 1 p zeta dash theta minus whole dash, and then boundary terms will vanish because zeta minus is 0 on the boundary. 0 to 1 q zeta and then zeta minus. And then expanding zeta as zeta plus minus zeta minus, what we reduce? Integration 0 to 1 p of zeta minus whole dash plus integration 0 to 1 q of zeta minus into zeta minus equal to whole 0. And then this is nothing but a of theta minus and zeta minus equal to 0. But what this implies? This implies zeta minus has to be equal to 0 from coercivity. And thus, if zeta is a solution, this implies zeta has to be non-negative on open interval 0, 1. Now, to show that this has a unique solution, we will have actually employ Lax-Milgram lemma. And since we cannot directly apply Lax-Milgram lemma, we have to again choose suitable spaces for this. So, to choose this, so we consider the problem. So if you consider this corresponding problem, so consider the auxiliary problem. This, then we know that A has a solution. So we are just transform the problem into another problem in a way so that it's now a homogeneous discrete problem. So A has a solution psi if and only if the problems I have earlier considered, the problem which we named as 5 and 5 has a solution zeta, which is zeta t, which is nothing but equal to xi t plus t. So we just transform our OD. Now problem A has a unique solution in view of Lax-Milgram lemma. Hence, we deduce that 5 has a unique solution. Okay, so far so good. Next, we will third part is check that U is non-negative on open interval 0, 1 and reduce that u dash 0 is greater than equal to 0 and u dash 1 is less than equal to 0. So to prove this, what we will do, we will actually uh, to prove u is to be non-negative, it's enough to prove that u minus is 0 almost everywhere. So testing v equal to u minus in equation 1 we get, so equation 1 was this only, the first equation you considered this thing. So we will substitute u minus as a test function, and u minus again will, since u has u is 0 on the boundary, u minus will again 0 on the boundary. So we will go to get integration 0 to 1 minus p u dash whole dash u minus plus integration 0 to 1 q u into u minus equals to f u minus integration again 0 to 1. And what this basically implies? This implies we have integration 0 to 1 p u dash into u minus whole dash plus integration 0 to 1 q u plus minus u minus equal to integration 0 to 1 f u minus. And as we know that f is non-negative on non-negative everywhere, and u minus is also non-negative. This implies this integration is non-negative, and this actually implies minus of integration 0 to 1 p u minus dash into u minus dash. So just expanding u as u plus minus u minus plus integration 0 to 1, and this will actually also end up becoming minus q u minus into u minus, and this is greater than equal to 0. So what this basically implies, this implies integration 0 to 1 p u dash u minus dash minus plus integration 0 to 1 q u minus is less than equal to 0. And this finally implies this is nothing but a of u minus, but since a is cohesive, this implies u minus has to be equal to identically equal to 0. And again, u minus is in h naught 1, and using the embedding in the one dimension, we deduce this is identically equal to 0, not almost everywhere. And finally, this implies u is actually greater than equal to 0. And when that is case, this implies u dash 0 is greater than equal to 0 and u dash 1 is less than equal to 0. The next part is prove that p at 1 times u dash 1 is integration 0 to 1 f xi zeta. So solution. So to get this, what we try to do, we multiply 1 by zeta and 5 by u. So to obtain, so first we're getting, since I'm multiplying 1 by zeta, this will give me integration 0 to 1 p. So after I'm just writing directly after integration by parts, p times u dash zeta dash plus integration 0 to 1 q u zeta is equal to integration 0 to 1 f zeta. And we have also one more equation. When I multiply equation 5 by u, I will get integration 0 to 1. And also, like here, when we use integration by parts, we are also getting u dash 1 p1 minus p1 times u dash 1, and zeta 1. And I know that zeta 1 is 1 only, so this I'm getting, and also integration 0 to 1 p u dash zeta dash plus integration 0 to 1 q u times zeta integration 0 to 1, and that is 0 only, actually 0 times u, so that is 0 only. So thus we have basically this sum of these two integrals to be 0. So these two integrals basically vanish. So this will implies minus p1 u dash 1 zeta 1, nothing but integration 0 to 1 f zeta. And I know that u dash 1 is negative, so minus of u dash 1 is nothing but, I can write in a sense of minus u dash 1 modulus. So u dash 1 modulus times p1 equals to integration 0 to 1 f times zeta. So this is what we wanted. Now, phi x is e raised to the power of bx minus 1 times, so I'm taking phi x with this thing. Check that if b is sufficiently large, then let me name this equation to be 7 minus p phi dash whole dash plus q phi has to be less than equal to 0 on open interval 0 1. So how do we check this, that this thing is less than equal to 0? We just compute directly. So I know that phi is this thing. So phi dash x is nothing but b times ebx, and phi double dash x is nothing but b square ebx. Once that is there, we just substitute the thing. So we consider minus p phi dash whole dash plus q phi. This is nothing but minus p dash phi dash minus p times phi double dash plus q phi. And this is nothing but, if I substitute the value of phi here, I obtain minus p dash b times ebx minus p b square ebx plus q ebx minus q. So this is nothing but ebx minus p b square minus p dash b plus q minus q. So now this follows directly, because I know that p and q are continuous functions, and in particular they are bounded functions, and we can use their bounds. And this b square will actually turns out to be a quadratic equation, uh, which actually depends on p and q, but we can have a good enough, we can choose a b in a form such that we have all of this to be less than equal to 0 for sufficiently large b. So we say in what follows, we fix b such that 7 holds And the sixth part is, let's take A to be e raised to power p minus 1 whole inverse. And then we prove that zeta is greater than or equal to a times phi on open interval 0, 1. So to prove this, we want to put psi equal to a phi minus zeta in 1. And to put this in 1, we need to actually prove that first thing, that this xi0 and xi1 actually has to be 0, or they actually vanish on the boundary. So psi 0 is nothing but a times phi 0 minus zeta 0. Zeta 0 is 0 only, and phi 0 is nothing but also 0. So this is 0 only. And psi 1 is nothing but a phi 1 minus zeta 1. And a times that is phi 1. Phi 1 is nothing but eb minus 1. And this is 1. So this is actually 0 only, because a times e raised to power b minus 1 is nothing but 1, and 1 minus 1 is 0. Thus psi belongs to h naught 1 omega h naught 1 0 1. Only need thing which have to prove, if you prove that we want to apply the part 1. So if you just prove that a of psi v is so let v in again h naught 0 1 negative, consider a psi v. So if you just prove that this a psi v is less than or equal to 0, I can apply the part 1 to deduce that psi is less than or equal to 0, and that will imply our assertion. So this is nothing but integration 0 to 1 p into psi dash into v dash plus q into psi into v. So what we do is we just plug in the value of psi there. Psi is a phi minus psi. So this is nothing but a times integration 0 to 1 p phi dash v dash so like before plugin we want to use this thing as well. So this thing about the about 5 that we approved, that we can have one beat node such that something holds. So this actually whole can be written as minus integration 0 to 1 p psi dash whole dash v, since again we vanish on the boundary, so the boundary term will not occur. And now we'll try to expand psi is equal to a phi minus xi. So 8 times minus integration 0 to 1 p psi will be phi dash whole dash v plus integration 0 to 1 q phi v. Then we have minus integration 0 to 1 p, and then we have left with zeta only. So this is zeta dash whole dash v plus integration 0 to 1 q phi into zeta dash phi into zeta into. But I know that zeta is a solution for this thing from basically from part 2, that theta has a solution for this thing, and not only that, once zeta is a solution, this integral is also vanishes. So this actually is nothing but zero only, since zeta is a solution from part 2. And for the first part, we know that this is nothing but what we have deduced earlier, that this b is chosen in a way such that this whole integral is actually less than or equal to 0. So, and v is positive. So we have this thing whole to be less than or equal to 0 from the earlier parts. And once that is the case, from part 1, we deduce that psi has to be less than or equal to 0. And once that is the case, we have zeta to be greater than or equal to a phi on open end of 0, 1. So reduce that. U dash 1 is less than 0. So from question 4, we know that so this implies that zeta is also not 0 everywhere. In fact, it is positive somewhere. And I know that p1 times u dash 1 is integration 0 to 1 f times zeta, which will be strictly positive because f is non-negative and zeta is actually positive everywhere except at 0. So from 6 we are getting this, from 6, and assumption on f we are getting this. Once that is the case, this will imply that actually u dash 1 is less than 0. Part 8 is check that u dash 0 is positive. So I will not prove this. This actually again can be deduced by initially, since we know that v satisfy 1, u satisfies 1, ut satisfies 1, if and only if vt is equal to u1 minus t satisfies 1 prime, and 1 prime is given as nothing but I want to write this is nothing but minus v dash whole dash is q v. There will be positive here, and then some g, and then we have v0 v1 again to be 0. So, and then we do the same analysis which we did for u instead of v. So instead of we did for phi instead of u, and we get that v1 will be again positive, and this will actually implies v1 is v dash 1 is actually strictly less than 0, and that will imply that u dash 0 is strictly positive. So we can do the same analysis. It's not it's just like not a new idea, just using the same stuff. So next part, fix delta in 0, 1, 0 to half. So small that ux whole divided by x is greater than or equal to half times u dash 0 for all x in 0 to delta, and ux whole divided by 1 minus x is greater than or equal to half times mod of u dash 1. That holds for all x in 1 minus delta to 1. So think about why such delta exists. This actually comes from the mean value theorem, or the continuity of u dash. Like you can check. Then let v be the solution of the problem minus p v dash whole dash is q times v equal to 0 on delta to 1 minus delta, and v delta equals to v of 1 minus delta equal to gamma, where what I'm taking the gamma to be, I'm taking gamma to be delta by 2 minimum of u dash 0 mod of u dash 1, right? And then show that u is greater than equal to v greater than equal to 0 on delta and 1 minus delta. So how do we show that? Actually, this comes from actually why the solution for this problem exists. Is a non-homogeneous distribution again problem. Again, can be handled in the same manner with the help of Flax algorithm. With the after suitable transformation, you can prove that this will have a solution. So once this has a solution, what we want to prove that u has to be greater than equal to this solution v of this new problem. So we want to use w equal to u minus v minus as the test function. So we actually show that w actually vanishes on the boundary. So if we consider u delta minus v delta, so this is u delta minus gamma, and gamma is nothing but delta by 2 minimum of u dash 0 mod of u dash 1. And once that is the case, I know that this is greater than equal to u delta minus delta by 2 u dash 0. And from assumptions and the continuity view, we deduce that this thing is actually greater than equal to 0 from the choice of delta, and thus w delta is 0 because we're taking the negative part. Also, if I take u of 1 minus delta minus v of 1 minus delta, this is nothing but u of 1 minus delta minus gamma, and this is nothing but again delta by 2 minimum of u dash 0 mod of u dash 1, and again this can be written as greater than equal to u of 1 minus delta by 2 mod of u dash 1. And finally, what we can do, we again use another estimate, so this actually can be written as u of 1 minus delta minus 1 minus 1 minus delta whole divided by 2 mod of u dash 1. And again using the choice, this is again greater than equal to 0 from the choice of A, from choice of delta. Now putting, so this will actually again implies that W of 1 minus delta is 0. Finally, putting W as a test function in 1, and if we name this equation to be star, we get so if I put it in 1, so it will be integration 0 to 1 p u dash w dash plus q u w is equal to f times w over 0, delta to 1 minus delta. But this thing is greater than equal to 0. And also we have this integration delta 1 minus delta v dash w dash plus p v dash, not v dash, just vw equals to 0, and taking the, this will be q actually, qvw, and taking the difference, we reduce delta to 1 minus delta v into u minus v whole dash w dash q into u minus v into w has to be greater than equal to 0. And once this will imply negative of delta to 1 minus delta p of u minus v negative part whole derivative, which is nothing but w only now, w dash q into u minus v. So negative will be there in both. And this will imply from nothing but a of w has to be less than equal to 0, and this implies w has to be identical to 0 by coercivity. And thus, but we reduce, we have u to be greater than equal to v. Moreover, we can prove that in a similar manner, v is also non-negative. In a similar manner, as what we proved for zeta, and zeta was the part number, it was part number third, yeah, part number 2, as in 2. So we have our result. Finally, the part 10 is something which actually we are borrowing again. This is we are not able to prove directly on the results we know, but I will state the theorem which we will use. So the statement is, it's a basically it's a first order differential equation with the with defined on a Banach space, and it has a property that actually you have a ellipsis function, so it's like sort of a Picard theorem only, but it is defined, I would say, on these Banach spaces and all, so it's like a generalization of that theorem only. So let me mention that theorem. So the theorem is, So actually, it is proved when we try to prove the Hilde-Virchow theorem. So it's like the sort of that. So let me mention this is known as a Cauchy Lifshitz and Picard DBA Banach space, and let F from E to E be a Lifshitz map that is, there is a constant L such that Fu minus Fv is nothing but less than equal to L times U minus V for all U and V in E. Then given any U naught in E, there exists a unique solution U in C1 of 0 to infinity E of the problem du dt by dt is its evolution problem, and U0 is U naught. So using this, it can be proved V is strictly positive on 0, 1, and for this basically once that is the case, U is again strictly positive on 0, 1. So this actually proves the strong maximal principle. So ultimately, the main idea which I want to present, it's like this weak formulation is not so hard as long as you know what test functions you have to try. And with an appropriate choice of test function, we can prove many results as we can see here. So with that, I will end my exercise session today. Thank you.